Okay, welcome back or welcome first time. It doesn't really matter either way. Hello. I am going over the chapter summaries for the introductory physics course, calculus based, college level. I'm using the textbook by Halliday, Resnik, and Walker, 9th edition, as my outline. All those books are pretty much the same. There's a couple that are different. The one that I really like is different, but I've already made summaries for those. So let's get to it. I'm in chapter 9, center of mass and linear momentum. Now, I'm going to start off this. They start off with center of mass. I'm going to start off with momentum. So if you have an object of mass m with some velocity v, we can define the following quantity. Momentum is the product of the mass and velocity. So since mass is a scalar, velocity is a vector, multiplying a scalar and a vector gives you another vector. And that is momentum. We use the symbol P for that. That's just what we always use. And this has units of kilogram meters per second, right? Because meters per second times kilograms. Okay, so why do we care about momentum? Let me show you. Let's jump back to Newton's second law. So before we wrote this, Newton's second law was F net is mass times acceleration. And we defined acceleration as dv dt, the derivative of the velocity with respect to time. So if I put that in, I get this. F net equals m dv dt. So all I've done is put in the definition of acceleration as the derivative of the velocity. Now, if the mass is constant, which it usually is, if the mass is constant, then I can actually move that in here, and I get dmv dt, right? Because if the mass is constant, you can pull the derivative out, the constant out front, and you get that. And there you see I have mv, and that's momentum. So this is dp dt. So now we have this, F net is equal to ma, or you could write F net is dp dt, the derivative of the momentum. And we call this the momentum principle. Principle, P-A-L, is a friend, right? Pal, that's how you remember that. It's not that big of a deal, though. And what this says, and I really like this way better, this says that what do forces do to an object? They change the momentum. And this includes situations where even if the mass is not constant, it still works. You need that for the rocket equation, which is covered in this chapter, but I'm not going to cover because I think it's too complicated. This also actually works even if you have super, super, super fast stuff where the momentum is not mv, but some people would call it relativistic momentum. We call it whatever you want. This still works. So this is a little bit better way to do it. I like this way better. But I think in the introductory course, in just about every single situation, F net is equal to ma, and F net as dp dt is the same thing. Okay, so that's momentum. Next is impulse. So they define impulse by just rearranging this equation. So if I if I multiply both sides by dt, I get dp equals F net dt. Now if I integrate both sides, I get delta p, right? Because I'm going to get the change of momentum from P1 to P2. It's going to be the integral from T1 to T2 F net dt. Or if you just want to look at the impulse by one force, you could just say this is equal to T1 to T2 F dt, right, for one force. And we call this the impulse. They use the symbol J for that. It would have units of Newton seconds, right, because this is in newtons and that's in seconds. And it's really the change momentum. I don't get too hung up on impulse. I mean, it's still just part of the momentum principle. Let me write if the force is constant, actually this becomes very useful. F net is delta P over delta t, right? If F net's constant F. This is really useful in a numerical calculation where you break a problem into small time steps and you assume the force is constant over that time step. Then you can use this to find the change momentum. Super, super, super useful stuff. I love it. Okay, let's talk about a system. And I don't really think this is the best way to go. You know, it's kind of weird connecting. Well, that's fine. Let me give a simple example here. So here's two masses connected by a spring, and they could be moving in some way, and there could be a force on this system. It doesn't really matter. This is M1, this is M2. It turns out that I can represent the motion of this complicated system, it's not even that complicated, by just representing this as one single point mass. And we call that, I'll put it right here, the center of mass. They call it COM, center of mass. And so let's just think about it this way. I could have my XY axis, I could have the position of M1 as R1, the position of M2 as R2, and then the position of the center mass as RCOM, the center of mass. And if there's no net, let's just say there's no net, F net is 0 on the system. F net is a 0 vector, then dp center of mass dt equals 0. Or the momentum of the center of mass is constant. So these two pieces can move relative to that, but the center of mass will not move. And so how do you calculate that center of mass? If you've taken a class with grades, which you may have done, and you have maybe tests and homeworks and quizzes, and they all are worth different percent, then you've done center of mass. It's a weighted average. So one way to write this, the best way to write this is simple. R center of mass as a vector, I'm going to write it as a vector. The book actually writes it not as a vector, is the sum of all the pieces. I could have two, but I could have as many as I want. So let's put the sum of I equals, let's just put over I. And we'd take each mass times its position. So I'm going to say MI RI. So I'm going to add up this mass times this vector plus this mass times this vector. And then I'm going to divide by the total mass, which is just the sum over I of MI. Now, if you want to do that just in the x direction, it would look like this. X center of mass. I would just have the x component of this. So I get the sum over I of MI XI over the total mass, which they sometimes use as capital M. So you can find that center of mass. Now, this is true for a distributed finite pieces in your system. So I could have 2 masses, 3 masses, whatever. If you have a distribution of masses like a stick, then I don't know, you should do this let's do this in one dimension. So this is in the x direction. Then I can take a tiny little piece dm right there, and it will have an x location x. Then I can say x center of mass is the integral from x1 to x2 of x dm over the total mass m. Okay. Now, I don't think they really get to that in this chapter. And dm doesn't even have to be constant. You have all these situations where you find the center mass. But if this is just a normal stick with a uniform density, you wouldn't be too surprised to find that the center mass is at the center. Now later, we're going to use the center mass for equilibrium problems of rigid objects, and you can see that the center mass is equal to the center of gravity. The center of gravity is equal to the center mass. So this says that I can pretend like there's a gravitational force acting on this, and it acts at the center. Okay, impulse, momentum. 2 things. I forgot the paper. Sorry about that. 2 more things. One of them I'm just going to mention. The next is collisions. and conservation momentum. So this one's a big deal. So imagine I have two objects. I'm going to call them A and B. And so A has a velocity, I'm going to write it as VA1. Let's write it as momentum. It has a momentum. It has a mass MA. And this, I'm going to write the momentum vector, PA1. And this one's moving this way, has a mass MB, and it has momentum PB1. 1 meaning before something happens, and you can see what's going to happen. They are actually going to collide. So here they are in contact with each other. And then during that collision, it's important to realize that B pushes on A. So I'm going to write this. F, B on A. But A pushes back on B. And because forces come in pairs, because Newton's third law, this force is equal in magnitude, FA on B, that's an arrow. They have equal and opposite directions with equal and opposite forces, right? They're the same magnitude, opposite directions. And so what does this force B on A do to mass A? Well, it changes momentum. So after the collision, maybe it's coming like this. We'll call this is A. This is PA2. And this is over here. I'm just picking PB2. That's B. And it got smaller. Okay, so let's write down the momentum principle for just object A, right? It comes over here, it experiences a force, FB. It's the only force acting on it. There's no other forces, and it ends up over here. So I'm going to say F net is FB on A, and that's going to be the change in momentum. I'm going to write that as delta PA over delta T. Right, the net force, B on A, change in momentum, change in time. Now I can do the same thing for B. I would just be FA on B is delta PB delta T. Now, because FAB is the opposite of this, so FA on B is equal to negative FB on A, right, because of Newton's third law, then these two, since these are the two, these have to be opposite of each other. So I get delta PA over delta T is negative delta PB over delta T. Now, delta T has to be the same. There's no way that this object can push on this for a different amount of time that that one pushes on that one. So I'm going to say delta T equals delta T. So those cancel. So now I have the change momentum of A is equal to the opposite of the change momentum of B, or delta PA vector plus delta PB vector is 0. The change in momentum has to be 0. Okay, and you think about that. If this is my system, and there's no external forces on that system, then the momentum will not change, and that's what we just said. Okay, now let's write this out a little bit more. Let's write this as PA2 minus PA1 plus PB2 minus PB1. That's a change in momentum. Final minus initial, change momentum, 0. Now I'm going to add PA1 and PB1 to both sides, and I get PA2 plus PB2 equals PA1 plus PB1. This is conservation momentum. This says that the total momentum before the collision is equal to the total momentum after. That's actually before. Before is equal to the total momentum afterwards as a vector. Okay, you can write this as an x and a y equation. Let me write this as an x and a y equation, just because if you don't want to deal with the vectors, that's fine. You don't have to. So I can say PA1x plus PB1x equals PA2x plus PB2x. B2x. PA1y plus PB1y equals PA2y plus PB2y. It's the same thing, just written as two equations. And maybe you want to get this in terms of angles. So let's just say I have this. I'm just going to draw the initial. I'm going to say here's A, and it's going this way, and this is going to be theta A, and then B is going this way, and that's theta B. So this is PA1, PB1. Then I can write this, PA1x is PA1 magnitude times the cosine of theta A. PA1y is PA1 sine of theta A. Now, whatever you do, make sure that in this particular case, if I have that as x and y directions, that should have a positive x component and a positive y component. This one should have a positive y component and a negative x component, just based on the way I've drawn it. So just make sure your signs work correctly, because sometimes when you pick these angles, depending on how they're defined, you may have to do that manually. So that's that. So, but you can find these in terms of the angles and find them in terms of the things afterwards. And this is conservation momentum. Nice, huh? But remember that this can only happen if what happened to my thing? Is it still recording? What the heck? Let's see if I switch. Okay, I think I'm going to do something I rarely do, which is stop and then edit two things together. Let's do that. Okay, sorry about the pause if there's any confusion. I don't know where it froze up. It just froze up. So the point I was trying to say is that this conservation momentum only works if Fnet is FBA, right? Only if there are no external forces. It actually works if there's more than two particles, that's fine. But you can't have any forces outside of the system. So just be clear. Okay, that's important. Okay, let's talk about collisions, because we actually have three kinds of collisions. Three kinds of collisions. And these work whether it's in 2 dimensions, 3 dimensions, or 1 dimension, doesn't really matter. But let's first look at this one called an inelastic collision. So imagine I have something like a train car A, and it's moving this way, and it collides with the train car right there that's stationary, and then this is my after the collision. After the collision, A and B are stuck together with the same velocity. This is an inelastic collision. So they come together and they stick, okay? And it doesn't matter if it's in 1 dimension or 2 dimension or whatever, that's an inelastic. Now, if I have no external forces or no net external forces, momentum is still conserved. So I can still say P1, I'll write it as this, P1 equals P2. This is the total initial momentum is the total final momentum. That's true. One of the things that we look at in terms of collisions is momentum and kinetic energy. It turns out that in this case, in an inelastic collision, the kinetic energy before KE1 is greater than KE2. Usually. There are some cases where you can get that different. So kinetic energy is not conserved. Next, we have an elastic collision. Let's think of it this. A, B, and then they're off doing something like that. So in this case, they do not stick together. And P1 is equal to P2. As long as there's no external forces, that's true. An elastic collision also says KE1 equals KE2. So the total kinetic energy of the particles before is equal to the total after. Okay, it's just there's no loss in kinetic energy. There's no loss in energy up here, but there's a loss of kinetic energy. It has to go into some other forms of thermal energy, deformation energy, or something like that. So that's different. And then we have, I just call a plane collision. So in a plane collision, you may have a car like this, A, and another car right here, B, and it's moving towards that. That's bad. And then they don't stick together. So they're both moving. They don't stick together, but kinetic energy is not conserved. So as long as there's no external forces, P1 is P2. That's that. Okay, one last thing. There's a whole bunch of stuff you can do with collisions. I love collisions. And remember, I'm not doing examples. I'm just giving the chapter summaries. The last thing is this idea of what happens if the mass is not constant. So if the mass is not constant, the example that we use is a rocket. So suppose I have a rocket in space. And this rocket has a bunch of fuel, and it shoots the fuel out this way. That's how rockets work. If there's some type of interaction that pushes the fuel out, there's a change in momentum of the fuel, and so there has to be a change in momentum of the rocket. So you can write that as a force. And the thing, you can get a thrust force based on the change in momentum. Now, the thing is, though, what happens is two things happen. As this rocket goes faster, the fuel actually has a less velocity with the background, with respect to the background. Because if it shoots it at a speed, they usually use something like u with respect to the rocket, but then the rocket's moving, then this fuel is actually going slower. The second thing is that as this shoots out fuel, the mass of this rocket decreases. So you want to write this in terms of the rate of fuel use of the rocket. It's a little complicated, and there's a couple little tricks. I'm not a huge fan. I will post a video about the rocket equation down below, but I don't think it's really appropriate for, I wouldn't do this in introductory calculus level physics course, but other faculty may. So I'll put that down below. Okay, again, just encouraging you that this is just a physics summary. Make sure you work hard, do a lot of problems, spend time. Learning isn't trivial. It takes time. So just keep at it. And I'll talk to you later. Bye.